presentation on behalf of Prof. Atangana, and the title of the presentation is Reproductive Momentum Unleashed, Harnessing Second-Order Dynamics to Decode Epidemic Waveforms and Predict Spread Patterns Beyond R0. This is Prof. Atangana's work, and I have the privilege of presenting on his behalf. As Prof is detained at the World Lawrence Summit in Dubai. I think he's also presenting today. He did send his deepest regards to the conference and his sincere apologies for his absence. So, as I've mentioned, the title of the presentation and the next slides we discuss the practical gap, what we want a new number to achieve. So the new number, okay. Well, I think the first slide is limitation of the reproduction number, the traditional reproduction number that we know. And normally we do that in epidemiology. That's what we do, the R0. So it is one of the most used number, or in most of the studies will use the R0, where we know there's a condition for it, whether we want to know whether there's going to be, if one person is infected, will in a susceptible population, will that one person cause more infections, or will the pandemic die out if there's one person infected? So we begin with a critical examination of the fundamental concept, the basic reproduction number, and its effective counterparts R0, RT. And then we know that these metrics are indispensable for determining inversion potential and providing an instantaneous snapshots of transmissibility. Okay, so however, for forecasting and intervention planning, the limitations are significant because R at T is inherently a first-order matrix. It quantifies the present velocity of an outbreak, but provides no information on its acceleration or trajectory curvature. So it cannot distinguish, what we basically say, it cannot distinguish between epidemiologically divergent scenarios, something like that. All right, so the gap that we're going to discuss or wanted to achieve, it should be able to detect directional or reproductive momentum, or to see whether there's the epidemic spreading up or slowing down, or ahead of the visible case searched, and also predict wave type, whether is it monotonic or isolatory, and also flag resurgence earlier than RT threshold allows. All right, and then also embed delay effects and trajectory curvature. So it kind of interventions that can be timed to prevent large asymmetric wave. All right, also provide a compact dimensionless signal usable for operational surveillance and early warning without discarding the intuitive of R0. Okay, so the damping oscillation. So rather than treating the epidemic trajectory simple as increasing or decreasing, we gain an insight by viewing the effect of the curvature of the infected component. Remember, in an SEIR model, this I will be the infected component, right? Component. So we start with the susceptible, the SI model, we start the susceptible, infected, and then the recovered. So the I will be the infected component. So we treat this IAT as a damped oscillator, a system whose future motion depends not only on its current level and velocity, but also on its acceleration and curvature. So the highlights is that I of t plays a role of a displacement. Signals whose velocity is instantaneous growth and the case slope. And then acceleration also captures the change in the slope, whether the epidemic is spreading up or slowing down. And then the damping term models law mechanisms, behavior change that reduces amplitude over time. A restoring term model for forces that pull the system back towards the equilibrium or perceptible replenishment or contact structures. So why this view matters? It matters because acceleration and curvature are predictive. So they contain information about upcoming turning points and the likely shape of future waves. Okay. So, so we know the mathematical intuitions and practical consequences. We know the second order presentation. So the first term here, we'll have acceleration, second derivative. First derivative will have the damping term, then the first one will be the restoring term. So, of course, the alpha will be um, the loss or control of strength, and beta will be the infection potential of the susceptible pool. Those are the two parameters that we already familiar with. And the sign of the characteristic determinant, which is D, determines the dynamics. So if D is less than 0, we know that we have oscillatory, which is a wave-like response. And then if D is greater than 0, or equal to 0, greater or equal to 0, we have an overdamped or monotonic return. So we need to monitor or monitoring only the I or the first derivative of I, it misses the lantern acceleration. Early positive acceleration warns of an coming surge before cases visibly arise. So traditionally, we'll only monitor these two. All right, so what we have now is the bridge, the gap that we bridge here is that we have a paradigm shift. Rather than viewing the epidemic incident curve merely as a time series, we reinterpret it through the lens of second order dynamics. That's the gap that Prof here was trying to cover. So so the model incidence I t by damped oscillation is given as that. I've already explained that the alpha will have this parameter alpha and the beta as well. So equation 1 becomes the equation 1 focuses attention on acceleration in addition to the instantaneous rate of change, which is the one that would use the first derivative, oscillatory solution, natural response to epidemic waves. So what we have now is what we call the RMI, which is to translate this theory into a practical surveillance tool. It was proposed argumentating the effective productive number with a momentum term. So one proposed form is the reproduction momentum index, which is this one, where alpha lambda is an scaling constant covering sensitivity of acceleration. This value here, okay, and then R of t is near 1. So R of t is near the critical threshold of 1. A significant positive acceleration can elevate RMIT, this term here, and then above operational threshold, providing an early warning signal rather than R of t alone. So this embeds the predictive power of the second order dynamics into a familiar index. So consider the following SEIR model that we know, normalized with n equals to 1. So we'll have it in this form. So the dynamics, this term, this variable, this parameter here allows the possibility of an endemic equilibrium. So this is a case where we have I is greater than this equilibrium point is greater than 0. So it opens the door to sustained or damped oscillations around the equilibrium point. All right, so what we see here is that, let's say this is the case where, let's say SEIR equals to 0, then we try to solve for the endemic equilibrium points. Then we linearize the S and the I subsystems about the equilibrium point. Then we have this Jacobian matrix. So this I'll just pass through because I know most of you are very familiar with this. And then we see that the values of A and B will be given by equation 12 and 13. So the connection, the connection phrase, this pair, A and B, plays exactly the role of alpha and beta in the damped oscillatory. Their values determine whether perturbation spiral or decay monotonically. Okay, so let's look at that. If we have an example here, with those endemic equilibrium points that we have discovered in equation 12 and 13, we see that, let's say you have, this is the term that we'll have, 15. If we have the parameters, alpha, mu, and beta, then S will be 2.25 and I will be 0.37. And so if we compute the discriminant pieces, we have the following values. So that we can conclude that 0.16 is less than, only given there on equation 18, is less than 2.4. So we are literally following the equation 15 there. So we have that the discriminant is negative. Okay, so if the discriminant is negative, we know the cases that we have to, there are 3 cases. The closed form solution of the perturbation. The first case, if this is greater than 0, we have real distinct roots. And if this is 0, we have double roots. If this is less than 0, we have complex roots or damped oscillations. So case 3, we can see that it yields a familiar exponentially damped sinusoid. Okay, so the Atangana strength number. So now we are going to discuss the Atangana strength number, which it's a dimensionless index constructed from the coefficients of the linearized characteristic equation of the disease model. So the Atangana strength number quantifies the balance between application and damping and provides a compact criteria for wave generation. So the first step, we formulate the disease model. So suppose you have that differential equation where X collects all X collects all the compartments, and X donates the model parameter. So X of X and this X. So you have all the compartments and then the model parameters. So the second step is to identify the master classes. So we select the minimal subsystem that governs the infectious dynamics, so which is the SI subsystem, and then denote the master variables governed by that, and then determine the equilibrium, which we did just now with the SEIR model that we know. Okay. Now we linearize the master subsystem about the equilibrium point, and we let Y to be U of T minus U star, and linearize the dynamical system, which will be of this form, where J is our Jacobian or Jacobian. And if the master system is two dimensional, the stability of U is determined by the eigenvalue of the Jacobian. All right, so now the eigenvalue satisfy this, just to satisfy this characteristic equation. And then for a two-dimensional Jacobian, we have a quadratic polynomial of this form, equation number 31, with the real coefficient functions ax, bx, determined by the trace and the determinant of J. Okay, now, if b of x is greater than 0, we assume for epidemiologically relevant regimes that it's a positive feedback product. So we define the next step, step 6. We define the discriminant that by this component, equation number 33, a squared of x minus 4b of x. So the oscillatory linear response arises when this determinant is less than 0. So the complex conjugate eigenvalues. So the Atangana strength number is given by a squared into x divided by 4b into x. So, of course, it follows directly from this form that if this delta is less than 0, if and only if a squared minus 4b is less than 0, which also implies that a squared over 4ab should be less than 1. If we assume that, of course, like I said here, assume that b of x is greater than 0. All right, so the interpretation of the Atangana strength number. So it is dimensionless and compares the squared damping like terms, a square, to 4 times the restoring like term, which is b. So if AT is less than 1, it signals a parameter regime where small perturbation produces isolatory, or the waves like decay or sustained circles if non-linearity allows. So Atangana strength number is not designed for time delay differential equation. You do not apply the delay-free Atangana strength number criteria when explicit delay appears in the model formulation. Okay, so let's look at this example. If we have a system of this form where we define A of x as the following and B as the following as well by question 36 and 37. So where our mu is the vital rate and gamma is the recovery rate and K is the extra removal or control parameter. So then the Atangana strength number will be written as follows, following from equation number 34. So if we put everything there together, we get that. And so the wave generation is predicted if this condition is met, as you saw here, that we need to have this term should be, the Atangana strength should be less than 1. Okay. And then for the model where A and B depend on equilibrium quantities, let's say the endemic equilibriums, one obtains the relevant representation, which is given by that. So remember the equilibrium points we had for the SEIR case. So this will be the Atangana strength number. So it will be under this mapping where A to be beta of I plus mu and B will be beta square SI. So this form highlights how equilibrium point prevalence and substability modulate the Atangana strength number. So if we have a low S or a high I, change the balance, and thus the wave, we have a wave potential. Okay. So, hello? Okay, in summary, so the Atangana Strength Number provide a compact local criteria. Hello?
Go ahead, sir. Go ahead, sir.
Okay. So it predicts the oscillatorily linearized systems, and then also secondly for computational flow, for computation flow and standard chain. So you have a model, the master classes, the equilibrium, the Jacobian characteristic polynomial, and then the Atangana strength number. So the Atangana strength number supplements but not replace conventional diagnostics like the R0. It supplements, it does not replace it. It specifically highlights acceleration-driven wave potential. So, so you need to use this strength number with caution because it is a linear equilibrium indicator, and it and is invalid in a delay-driven formulation unless re-derived appropriately. Okay, so this will be the procedure that one has to follow when you are dealing with, you want to apply the Atangana strength number. So if you have an ordinary differential equation, then you have to define or identify the master subsystem. You compute the equilibrium point and linearize, and you do your Jacobian, then you obtain the trace, the determinants, and then you can compute the Atangana strength number. So if we have, for instance, you have a system with demography. So you have a model of this form, same SEIR model. So the master subsystem will be SNI. So the endemic equilibrium point will be, of course, where I is the equilibrium point of I will be greater than 0. So this will be the equilibrium points. And the Jacobian related Jacobian to be of this form, then our trace will be given there by the trace and the determinant will be given by equation 47 and 48. So same applies if we have a system of this form, the SEIR, which is the susceptible, exposed, infected, and recovered. So if you have 4 compartments, so here this will be your master subsystem, E, and the exposed and the infected group. So in this case, your equilibriums will be given by that, and your Jacobian will be given by 55, and then your trace and determinant will be given by 56, equation 56 and equation 57. So the strength number in this case will be given by the following equation in equation 58. All right, and then if you have a SEIS, this is also a bit similar, but so you'll have a Jacobian of this form, and then with A given as this, B given as this one, so is C and D, and then the characteristic polynomials will be given as follows, equation number 61, and then the Atangana strength number follows also to be in this form. Of course, we know the values of A, B, C, and D, which are given the equation number 60. All right. Now, same applies with SIR S. So you'll obtain the Atangana strength number in a similar fashion. All right, so what happens now if you have a perturbation form and the three regimes? So the perturbation equation of infectious perturbation, I, it will be given as this form. Then it has a characteristic polynomial of this form, and then the Atangana, we have defined it to be this. So the three regimes will be, if this is less than 1, we have underdamped wave. If the Atangana strength number is equals to 1, we have a critical damping. And I don't know, my slide is not showing. So the first case, if the strength number is less than 1, this is the case where if a squared is less than b over 4, so the roots are complex. So the biological interpretation of this will be, we have repeated epidemic waves with decaying amplitudes. So this will be the biological interpretation of the first case. All right. The second case, if the Atangana strength number is equals to 1, we have a critical damping, which means we have double roots in this case. And then this just mean that, so we have fastest non-oscillatory return to equilibrium. At most one prominent peak, then monotonic decay. Okay. So then now the third case is if it's greater than 1, we have two distinct real roots. So this means we'll have a monotonic return. So there won't be any other waves. So we have a strong damping dominance restoring forces. All right, and then so the practical notes for applying the Atangana strength number. Of course, the first one is that the Atangana strength number is a local diagnostic. You pair it with the nonlinear smart simulations for global behavior, and you estimate coefficients A and B, either from the model linearization or by short window fitting of observed the compartments S and I dynamics. So you always have to present the uncertainty bounds. So also another one is that it complements, like I've said before, it complements the reproductive number, which is the R0. So R0 answers the invasion potential, and then a Atangana strength number, it partitions post-inversion dynamics into isolatory or monotonic regimes, essentially for intervention timing and preparedness. Let's say maybe if you have an outbreak and all that. So we study whether the Atangana strength number can be used to detect the half bifurcation in polars in planar systems by monitoring the trace and the determinant of the Jacobian All right, so we have to say we consider this planar Jacobian depending smoothly on the parameter mu. So we have that Jacobian there with the following trace and the determinant. So in this case, the Atangana strength number will be given by equation number 79. So now what we claim here, we claim that if the half bifurcation occurs at mu c, then our trace will be equal to 0, the first case, or the determinant will be equal to 0. This will imply that the Atangana strength number will be 0. So we also have transversality reduced to this point, dt over du should not be equal to 0. For mu near this value, mu of c, the Atangana strength number should be less than 1. This one implies that we have complex eigenvalues, and the Atangana strength number approaches zero, signals approach to the half bifurcation. So if you have then you can have the first step, of course, you get the eigenvalues and the discriminants. So, and then also the classification that if the determinant is less than zero, you have the complex conjugate eigenvalues. So you'll have a focus or spiral, and then so we look at equation 82. So that's the case what the Atangana strength number implies, if and only if the determinant in this case is less than zero. And then also equation 79, we have the following in this case, that the Atangana strength number in this case it will be zero. So so the other case also is that we'll have that the monitoring Atangana strength number, which is given by this near U mul of C approaches zero, occurs when T approaches zero, non-zero dt over the mu ensures that the Atangana strength number crosses through zero linearly unless the determinant simultaneously vanishes or is excluded. So let's consider this worked example. If you have that dynamical system there given by 87, then the Jacobian at the origin. So we have our T and the delta given by 88. So the Atangana strength number in this case is going to be given by equation 89. Okay, and then so now let's see the practical implication and the usage. Okay, so for detection, we track this value, the Atangana strength number, along a continuation path. So the strength number decreases if the determinant is greater than zero, efficiently flags the half threshold. And then also we have precursor signal and caveats. And what here I can mention also is that the Atangana strength number evolution complements the standard bifurcation analysis and provides an intuitive scalar monitor for approaching oscillatory instabilities in planar epidemic models. So we address two questions at the equilibrium point. The first one, can the Atangana strength number recover the classical inversion threshold using given or usually given by R0? So can the Atangana recover the classical case, which is the reproduction number R0? So okay, and then the second question is, under what exact condition does the Atangana strength number give the same outbreak or die out signals as R0? So the approach is to linearize at the differential the DFE form, the infection block characteristic polynomial, compute the Atangana strength number at the disease-free equilibrium DFE, and compare its sign or behavior to that of the reproduction number, which is the R0. Okay, so in this case, if we have that system that we saw earlier on, so we know for sure, in this case, the reproductive number is given by this. This is, I'm sure most of you are familiar with this already. So if we linearize, some of this stuff I can't really clearly see. If we linearize and follow all the steps, and then we try to compute the Atangana strength number at the disease-free equilibrium, we have the following equation. And then for the second case, for the SEIS, this is what we have. The reproductive number will be given by this. And then in terms of the Atangana strength number, it will be given by equation 106. So we do the same also for the SIRS. And we see also that this is where the R0 will appear there in equation 110. So we conclude that R0, if R0 is greater than 1, if and only if the Atangana strength number is less than 0. Okay, and then in this case also, I think I didn't discuss this one. We concluded that R0 will be greater than 1 if and only if the Atangana strength number is less than 0. All right, so we have this table here. Remember the cases that we have considered: the SIR, the SEIR, the SEIS, and the SIRS. So these are the all well-known reproductive numbers. And then the Atangana strength number or associated to the SIR, we just discussed also, they are given here. So the condition is that if R0 is greater than 1, then it implies also that the Atangana strength number will be less than 0. If R is greater than 1, the Atangana strength number will be less than 0. If R0 is greater than 1, then it will be, the Atangana strength number will be less than 0. And for this case, if R is greater than 0, we will have that the Atangana strength number should be less than 0. So now the interpretation: what or when does the Atangana strength number match R0? So R0, if it's greater than 0, if it's greater than 1, we know that the Atangana strength number is to be less than 0. So the reason for this is that infection block or determinant flip sign at the inversion threshold. So the algebraic manipulations express the Atangana strength number in the form of proportionals to R0 minus 1, 1 over R0 minus 1, or R0 minus 1, reproducing a negative Atangana strength number when R0 is greater than 1. So practical implication means that the Atangana strength number that we evaluated at the equilibrium points recovers the classical inversion sign for these models. Therefore, the Atangana strength number can serve both as a wave pronaensis index near equilibrium equilibria and as an inversion indicator at the disease-free equilibrium via the signs, of course. So anyway, we have the limitations and the recommendations. In conclusion, we see that Prof. Atangana's work introduced a formal framework based on second order dynamics and proposes the strength number and as a novel dimensionless epidemiological diagnostic. So interpretation depends on the value of ASN, Atangana strength number, and also the local diagnostics for strong nonlinearities, multi-stability or explicit delay, complements the Atangana strength number with nonlinear simulations, normal form calculations, or delay aware analysis. So the bottom line here is the Atangana strength number unifies inversions and wave, as I mentioned before, but the interpretation must respect the evolution point, okay, and the model structure as well. And then this will be the case from our four canonical models. We obtain the following, that if the Atangana strength is less than 0 and the reproduction number is greater than 1, we have an outbreak. And if this Atangana strength is greater than 0, that means the R0 will be less than 1, then the disease die out. And the Atangana strength number, as it goes to positive infinity, then R0 will be equal to 1, which is the threshold. So the Atangana strength number condenses both the inversion threshold and the dynamic model into a single compatible scale. So in essence, R0 answers, can inversion occur? And then the Atangana strength number, it answers, how will it unfold? Is it going to be a wave or a monotone, a growth or a decay? So I think I'll end here.